Hello, welcome to Forest Learn. In this video, you can try a 1-mark question on simple harmonic motion and impulse. Once you've had a go, we'll discuss the solution so you can check your answer. In case you don't know, simple harmonic motion is usually just abbreviated as SHM, so I'll probably just be saying SHM throughout instead of simple harmonic motion. Let's take a look at the question. A particle of mass m is performing simple harmonic motion, SHM, with amplitude A and time period t. See displacement time graph below. What is the impulse given to it between t equals 0 and t equals capital T over 4 in terms of m, a, and capital T? Please pause the video and have a go at this by yourself. When you're done, unpause the video and we'll discuss the solution. Okay, welcome back. To answer this, we of course have to recall what impulse is. Remember that Newton's second law, F equals ma, can be expressed equivalently as follows. F, the resultant force, is equal to the change in momentum of a particle divided by the time taken for that change. Or in other words, the resultant force acting on a particle is equal to its rate of change of momentum. Now if we just rearrange this, the impulse is simply given by the product of force times time, or change in time, or time interval. Or equivalently, the impulse is simply equal to the change in momentum that the particle or object undergoes. Now recall that momentum is simply given by mass times velocity. So this change in momentum, we can express that as m times the final velocity, call it v2. So mv2 is the final momentum, take away the initial momentum, mv1. So we're calling the initial velocity v1. And we can express this equivalently as m times the change in velocity. So to work out the impulse between time 0 and a quarter of the time period, we could just look at the left-hand side here and try to work out force multiplied by the time interval. But a problem with this approach is that the force, or the restoring force, is not constant. It changes as the particle moves. So if we wanted to go down this route, we would effectively have to work out the area under a force time graph. A simpler route is to consider the right-hand side, is to consider the impulse, or work out the impulse from trying to figure out the change in momentum, or mass times the change in velocity. Recall that the velocity of the particle is given by the gradient of the displacement time graph, and will look something like this. Now remember, the displacement time graph is a cosine graph, so the displacement is given by the amplitude multiplied by cosine of omega t, where omega, the angular frequency, you'll recall, is equal to 2 pi divided by the time period, capital T. And the velocity, as I mentioned a moment ago, is given by the gradient of the displacement time graph, or using more mathematical speak, it's the derivative of the cosine graph. And if you know a bit of maths and you've studied derivatives of trig functions, you'll know that the derivative of cosine is minus sine, but we get this extra factor as well of omega out at the front. The biggest that sine omega t can be is plus or minus 1, which means that the biggest values of the velocity are going to be plus or minus omega a. In other words, omega a, hopefully you recall that this is just the maximum speed, Vmax. So we can add this to our graph here. The maximum velocity here, or the maximum positive velocity, is omega a, and the maximum negative velocity is minus omega a. Okay, corresponding to here and here respectively. So to work out the change in velocity, we just need to figure out what's the initial velocity at t equals 0. Well, from the graph, that's just 0. So v1, the initial velocity, is equal to 0. The velocity at a quarter of a time period, well, that's just here. That's the maximum negative velocity of the particle, which as we discussed is minus omega a. So v2 is equal to minus omega a. And what this means is that the change in velocity, v2 minus v1, is simply minus omega a. So to work out the impulse, which is just the change in momentum, we just do the mass of the particle multiplied by the change in velocity we found. And since the question wants the answer in terms of ma, which we've got, and t here, we just have to replace omega, the angular frequency, with 2 pi over t, and we're done. So the impulse is simply minus 2 pi m a divided by t. If you found this video useful, please like it, share it, and subscribe to the Forest Learn channel if you haven't already, and leave a comment. I'd love to hear from you. Thank you for listening, and I hope to see you soon.